So Mahmood, you can start. You can start and
Okay, yeah. So one thing that we were working on from the last meeting is the idea of like how can we represent the CCD error in a quantified number. So that's one. And other than that, I was also trying to see like how the other like unsupervised machine learning method works other than the GMMs. I was just trying to see like how they are working, like just to have some basic idea of like how they're working, something like that. So this is why I actually look for the DB scan, like how DB scan actually works, and I also look for the like the upmask to understand like what actually working inside of the upmask or something like that. So I was trying to reading that paper of the upmask paper. I think it was written by someone in Portugal. Uh, so I found that DB scan is actually a little bit easier to understand. So I can share. Can you see my screen?
yes, all good. Yes, yes, we could see your screen. You can share.
Okay. So what I found is that in the DB scan, like what they do is that we need to have two parameters. Like one parameter should be epsilon. So this is more like radius, and there is another parameter like which is called minimum sample. So mean sample like that. So what happens is that we have a many random points going around, and the main assumptions that they are having is that if we have a cluster or if we have actually a range of things like maybe a cluster or maybe the member of something or something like that, they will always stay very close to each other. So that's the like major assumption. So they are saying that because they will stay in the same place, what we can do is at the very start we can pick one point at a random. So suppose we just pick this point at a random, and then epsilon is more like a radius things. So we will make a circle of epsilon around this point, and then try to see like how many points I have inside of this circle. So here I have like 1, 2, and 3 points, and so I have 3 points inside of this epsilon circle. And then this minimum sample things is telling us like what is the minimum number of sample we want to actually say that there is a cluster or there is not a cluster. So suppose our minimum sample was 5. So we can say that okay, it is not part of any cluster yet because the like epsilon circle has only 3 members inside of it. So then we will randomly try another point. Maybe we'll try with, let me change my color. Maybe we'll try with this point, and then we'll again make a epsilon circle. And when we make an epsilon circle, we can see that there is 1, 2, 3, 4, 5, 6, 7 points inside of this circle. So we can say, okay, so this red one is actually part of a cluster. So we will say that, okay, this is one cluster, and we will select the members that we found around it, and we will like give you different color. And then what we will do is we will go around with each of these things. Like now we will make a circle around each of this circle of each of this green circle, and see like if we can find a circle where we have more than 5 members inside of this circle. So we will continue this
How do you
process.
define the size of the circle?
The size of the circle is epsilon.
Some epsilon
Oh,
you take.
oh okay.
You define a parameter,
Oh,
however big or small.
Yeah.
oh.
So what happened is that so ultimately we will found some point which will not be part of any cluster or something like that. So you see there is 1, 2, 3 points which are totally isolated. So for this value of epsilon and for this value of minimum sample, like we don't actually have any member around them. So we will just keep them like by themselves. So we will say these are isolated points, and we have a cluster here. I can change the color. So like this was our cluster. So we can say, okay, we found one cluster and we found like some isolated points which are there. So this is how the DB scan like works. So we can tweak the parameter like the epsilon parameter and the minimum sample parameter, and try to see like when we are getting a good value and when we are not getting a good value, something like that. So I found a very good like article on the DB scan. Let me show that. I am sharing my whiteboard. Share this. Okay. So you see that we can make some arbitrary point, like suppose first I can make some Gaussian mixture. So you see, like these are my circle, like these circles are my
Now,
like
can you
epsilon
share this
circles.
URL? Can you share this URL?
Yeah, sure. So I share it in the chat, and I'm also going to
Yeah,
share
yeah.
it in WhatsApp also. So
Put it on the WhatsApp thing also.
these red circles are my epsilon circles. So if I increase my value of epsilon, then the circles value will be like increased, and this is the minimum points I need to have if I want to say, okay, this circle is a part of a cluster. So if I make this very small, then like now my minimum points is 1. So if there is only 1 point inside of my epsilon circle, I will say that, okay, so this is part of a cluster. So this is why you see that this also becomes red. And so usually people start with 4 and then play with around it. So when we will start the model, what will happen is that arbitrarily they will choose a random point here and then make an epsilon circle and then try to see like if there is any circle I am getting where the minimum points is where the total points instead of the circle is greater than 4. So let me small the epsilon a little bit and then we press grow. Yeah, so here it will started doing that for each and every one. They did that. Okay, so you see this is an okay, I got that then also. And then after I finish this, it teaches us the process from the other remaining points. So you see every time, like once I got a member, and so you see like this one is not part of any cluster because the distance from like this point to the other points is a little bit higher. So if we change the epsilon value a little bit, maybe 1.4, 1.5, we will capture both of them. And so it gives me actually for other things also. Suppose this is my this. So if I start it, so it will, oops, sorry. It will start from a random place. It will start from a random place and then it will move around. So it will first move around along all these points that it gets around this circle and until norm leaves. And then it starts randomly from another points.
I think.
So it will complete this whole circle because the distance is not high. Like if I now make the epsilon circle very small, I guess this will go to, it will go stops because my epsilon size is now very small. And if I make this very large, then there is a chance that maybe I will get these points also, possibly. Yeah, so like, and if I just see one last one, like, so this is my density ones. And now if I start the, oops, sorry. So I am starting with epsilon 1.2, 1.1, and minimum points is 4. So it will start from there and it will go around with it. So you see here, they are measuring the Euclidean distance as they, like when I'm saying the epsilon is 1.10, in a 2D space, it will make a circle. In a 3D space, it will make a sphere. And every time it will try to find out the Euclidean distance between the points and see if the distance is like less than the epsilon or not, something like that.
So how do you converge to the ideal value of epsilon?
So what people do is that, they run it with different value of epsilon and different value of minimum samples, and then they try to see, like they measure a matrix, like specifically if I told, in the context of like in the context of open cluster membership, what people did is the same thing that other people did, like they change the value of epsilon and they change the value of the minimum samples, and they see how the CMD looks like for the member that we got. The CMD looks better, then they say, okay, so this value for epsilon and this value for minimum samples is working nicely, something like that. So usually they make a, so what they do is So what I found in most paper that they make a matrix and then they plot a epsilon value here and
So that means they fix the values of epsilon and minimum points based on CMD.
can you say it again?
I'm saying that means they are fixing the values of epsilon and minimum points based on the CMD.
Yeah. So like they are choosing the CMD as a matrix here, or in other contexts, the matrix could be any other things. Like maybe we can also choose a, like once we got the two cluster, maybe the member and the field cluster using the DB scan, we can do the histogram of them. So similarly, as GMM, we should expect that the standard deviation for the field star should be very high, and the standard deviation for the member star should be very low. So we can also use this as one of our metrics to choose the value of epsilon, like which will be the optimum value of epsilon and optimum value of minimum samples. So this is the like basic things people try to do. Like so they choose a matrix and they plot the matrix versus epsilons and see like how it is. So usually the plots are going like this, like it increases up to a point and then it starts decreasing, something like that. And then I can make a plot of, I can make same plot with different minimum samples. So maybe when I change the minimum samples, my graph just move a little bit. So maybe this is another for another like minimum samples. So maybe for this, my minimum sample was 5, and for the yellow one, my minimum sample was 4, and for the red one, my minimum sample was 3, something like that. So they make a plot of this, and then they choose the value where the desired matrix is the higher or the lower, like whatever is better. So they use the matrix to choose the optimum value of epsilon and optimum value of the minimum samples. So I also found that this is one, I'm not sure if we can say it in limitation. Like, so you say in the supervised machine learning method, like random forest that we did last time, or any other supervised machine learning method, because we will always have a training data in our hand. So we can use the training data to optimize our parameters. So we optimize like all the parameters of the random forest using the training data itself. So we are not using the real data to change our model or to tweak our models or to make our model working better. So we can training data to make our model as optimal as possible, like choosing the optimum value of the hyper parameters, and then run this model in the like real data. But for the unsupervised method, like most of the time we don't have a like real data or training data. So most of the time people did is they use the real data to like make an optimum value of the hyperparameter and then make an optimum model for this. And this also, like, it's also true that because we're using the real data to change the model and then using this model to say that, okay,
Yeah, Ishan.
working nicely in this real data.
Ishan.
Yes, sir.
Good. So,
Hello. Can you hear me?
Yes, we can hear you, Mahmood.
Okay, yeah. So like that's the thing. Like maybe it's just one small limitations of unsupervised methods.
I think this will be good also because this does not impose a Gaussian this thing, na? So the problem that
Yeah.
we were
So
having for these
that's
non-relaxed clusters. So for actually for DB, I know that for especially for youngsters, a lot of people use DB scan. Somebody I was doing some work with also, she was using DB scan because in young systems especially you don't have Gaussian this thing, na? It's not virialized and all that. So then
yeah.
you have a good scatter. So.
So
And
in the
generally,
DBs,
open clusters are not like globulars, right? Globulars will be better off with Gaussian, but open, I think, will be better off with DB maybe. No?
yeah, that's true. So like this is the one advantage of like DB scan. Like we are not assuming any Gaussian distribution. So we don't like care if it is a Gaussian or not, as long as they're staying together, staying close enough. we can use DB scan to find them. So that's one advantage. But one limitation of DB scan is that you see, like, the major assumption is that our cluster members in their particular variable has to be like close, which is true, like they stay close, like the proper motion stay close to one another, something like that. But also the field stars, then like we need to keep a value of epsilon in a way so that we don't take the like field stars value. And the problem is in the real world, like the member and the field listers, like this difference is not very strict cut. So like it's true that maybe if we make a PM array PMD plot, then all of my member will be lying very close to each other, something like that. But then we will also expect some field listers which will maybe lie here or there or there or there. Maybe they will just uniformly distributed all around the places. And because of this uniformness, some of the field listers will be stay there. And now if we don't choose a epsilon value very wisely, then what will happen is that we will end up taking like some of the field stars because they are just in the border of my member stars. So that's one thing we need to be cautious about, because it's like a chain reaction. Once we got this point, we also need to make a circle around this point. So we will take more point around it once we increase the search radius or something like that. So this is one thing to keep in mind. But that's true that because we're not assuming anything Gaussian, it will work better without any Gaussian distribution. That's one. And number two is, you see, in the GMM, we have to give some very strict cutoffs in the PM array, PMDEC, and in the parallax space. Because if we don't give this cutoff, then GMM will not work. But for the DB scan, we don't necessarily need these cutoffs. Like we can make our search radius as high as we want, something like that. So like that's the basic things I got for the DB scan. But yeah, like we need to run it for some clusters and see how it looks, and then we will understand what it looks like and something like that.
Yeah, so actually I Googled and looked for this thing. I found one. So there is that group which is a very active group which has done looking for clusters, but there's another one which I found, open cluster detection using DB scan. I've shared that link with people, and this guy has his code on GitHub, but it's basically star cluster detection.
Yeah, like DB can also use for detection and also use for like membership. And then the good thing is for the DB scan, like because it's one of the common machine learning methods, like we already have the code in the SciPy learning things.
That's it.
That's one good thing. Unlike the other one, like you see when you see in the upmask, I found the code of the upmask, but because the upmask is not necessarily a machine learning model, like it was created, like it was modified specifically because of the cluster member detection. So it was made by them, and they write it originally in the R language, and then people use that context to change it to the Python. So
But Mahmood, for this one, do we need to do like, remember in GMM what we had to kind of filter our data, right, to reduce the field stars. So with DB scan also, do we need to do some kind of cutoffs and filtering before we run it, or?
maybe DB scan might have some pre-processing, like just like any other method. But unlike the GMM, I don't think we need to give any cutoff in the proper motion or in the parallax space just to make sure that we don't have enough field stars, because we're not assuming anything Gaussian. That's not a problem. Like as long as our cluster members are staying together, we can take a very large search radius. That's not a problem. Like our proper motion space could be higher, our parallax space could be also be very higher. So as long as the so like suppose if I make a histogram of parallax, so suppose I'm taking all the parallax value up to very high range, but as long as my member stars are very staying very high here, so like these are my member stars, And as long as they are very high, like they are very dense, we can take a very long range. That's not a problem with DB scan. But that was a problem with GMM.
So now the next exercise we should do is to run DB scan on M67, 64055, the same ones that you ran it for those ones. We can run it so
Yeah,
that
so
that
like,
will give us a comparison.
yeah, that's actually a good advice because
Because that's what we're
initially
trying to explore, right? We are trying to explore an optimizable method, right?
yeah,
So the ones which are available, which are there in the market, we need to check them out, right, first. And then we can see how can we further optimize it, right? But first we need to use
yeah,
the basic ones, see what are the results we are getting, and then we can see how can we fine tune any of these to get even better results, right?
yeah,
Like again in this, will filtering help out? Another important thing which I wanted to say is that in DB scan, see, you can do it either in the proper motion space or in the real space sky coordinates, or you do it with all those coordinates. Do it in sky coordinates, proper motion coordinates, parallax coordinate. Use 5 coordinates and do it like that. But then you'll have to do some kind of normalization, right?
yeah, of course.
So you'll have to normalize it, and you normalize it, and then you can do DB scan in this 5 dimensional space: sky coordinates, proper motions, and parallax, right? And see how that
Yeah, I was
works.
actually thinking that maybe we can try with only like the PMRA, PMDEC, and the parallax because like because we're dealing with the open clusters and most of them are quite young. Like I'm just thinking that maybe like if we take the like RA as our parameter, then we will confine ourselves in a very small space, something like that. So we want
That's
all
it.
investors to lie very close to each other in a spatial distribution. But if it can be possible that maybe some members are actually maybe they're not lying exactly very close to each other. Maybe there are some kind of structure, or maybe there are some members which are going a little bit away from each other, something like that.
Mhm.
Try, yeah, that's true. We can try.
Otherwise, what did you have in mind?
I was thinking that maybe like because at least no matter like what happened to the like mass distribution, or no matter what happened to the like structure of the cluster, or maybe escape member or something like that, if they're member of the cluster, they must have a similar kind of proper motion, and also they should be lie in the same distance from us. And I guess
Correct.
we also have the similar radial velocity, but we don't have that data.
Yeah.
So
What sky coordinates you have?
yeah, like sky coordinates we have, but I was just thinking that I don't know, I was thinking
You can look for radial velocity data for some stars for what it's available, and use that to have more confidence on membership. But that would be depending on which spectroscopic survey you're using, and you'll have to check that out.
yeah. And another thing that comes to my mind, like which I learned from like understanding the GMM things, like while working on the GMM, is that you know I was thinking maybe it would be a little bit better if I search for some paper where they use DB scan to do open memberships and then try to replicate them. So if I try to do that, then I will understand, okay, so what are the filter that they use, and what are the like things that I need to keep in mind. And these things maybe didn't come to my mind automatically, but when I saw the papers, then I will say, okay, so this is the things I need to do before I run the DB scan, because if I don't do that, then this type of problem will arise or something like that. So I was thinking to actually replicate some paper first, and then once I done with the replication, so I know which filters are like necessary to give before the DB scan, before running the DB scan or something like that, then I can run the DB scan using this like filtering for the M67, NGC2264, or the one that we run GMM, so that we can compare between them.
Yeah. That's right. We can. But there are, I know, I mean, there's this lady with whom I was trying to do some work, but she actually did YSOs, young stellar objects, with DB scan. But this paper, I can show you this one. Uh, but these are young stellar complexes, and
Um, did you share the link in WhatsApp?
yeah, one sec, I'll just share it.
Oh, yeah.
So the second author, she had actually come to Hyderabad also, Estelle. And even I went to her in France. She's in Grenoble. And we actually thought of doing something, but then COVID came. So I've shared that paper over here, which is they did it for young stellar objects to actually look for clustering in young stellar. But this is obviously not using Gaia data or something. This is using data which you have for YSOs, and you use that to identify a dynamical evolution and stuff like that. But I'm a little confused that if we are going to do it for Gaia data, if you don't put any filters and you're getting everything, then I think it should be a little difficult to get a good DB scan result. I don't know.
Because we have so many data.
Yeah, maybe that's what I'm saying. So we try it out for some clusters and we know how it's working out, whether you need to do filtering or not filtering, right? But
Yeah.
yeah.
And the one thing I also found quite interesting while looking for this is that some paper, like specifically the Atmas one did that, and some other paper also did that. So you see, like, because it's hard to give a matrix on the real data, so sometimes it becomes a little bit difficult to, because of the error of my data or because of the distribution of the data, something like that. And then what they did is that they make a simulated cluster, and then they run these models, like specifically the paper where they compare between compare between two or more different model. So what they did is that they make a simulated cluster, and then they run this 2 or 3 or 4 model in that particular simulated cluster, and then they see how it works for all of them. And then they try to give a discussion about, okay, so this is our simulated data, and this is how it looks in this for these specific models. So it looks like, at least for the simulated data, this model is working better. And then they are applying it on the real data to make some more like insight or something like that. But initially, the main matrix was used in a simulated data set, something like that. I found it doing in the UpMask one. I also saw it maybe. There was a paper on, they are trying to find out the galaxy cluster member, and they are trying to exploring 3 or 4 like machine learning methods to see which one working nicely. And they try to do that. They try to make a simulated galactic cluster and see how it is working for them, something like that. So how good approach is that? Like making a simulated data and then run it there. Because I was thinking, like we can argue in both sides. Like if we make a simulated data, it's easier to make the matrix, and it's easier to actually see which is working and which is not working. But on the other side, because we're using a simulated data, we're not necessarily taking the accounts of all the nuances we are getting in the real data.
Yeah, but simulated data has the advantage that you know what you've simulated, right? So then you
Yeah,
know what you're retrieving of what you put in, right? While in real data, you don't know actually what it. So I mean, both have their advantages, obviously, Both have their advantages and disadvantages.
Yeah, like you see in the, so when we run the GMM in the M67 or some other papers, so we need to see the CMD and the parallax histogram and the PMRA, PMDAC histogram, and then make a comment that, okay, maybe these are our filter and maybe these are not our filter, something like that. But if we have a simulated data, then we already know that, okay, so these are our member and these are our non-member. So we will immediately know if this model is working perfectly or maybe better or maybe or something like that.
Yeah, I actually, what I look at it just now, I think both have their advantages, simulated as well as real data. Both have their advantages, especially now when we want to compare these different clustering algorithms, right?
Yeah,
Because, but maybe I think maybe you can start off with M67, 6405, 581, the same three that you were doing, and then we can have a look at that. Meanwhile, we can read up a little bit on these things because so that we get a feel of.
yeah, sure.
Yeah. Hmm. What do you have to say, Mudassir?
I think it would be good if you read about these things first, then try to have a look.
So I've shared that one DB scan paper. Then that other one is also there. I've put it all. It's all on the WhatsApp thing.
Okay, ma'am.
So you can try all of them. DB scan that and upmask. Upmask. Did you try Memo? Upmask.
Yeah, so I looked how the Atmos working. So it's actually quite interesting, like, and it's complex than I expected. So what they did is that they, because the original Atmos one, they use the like color data, photometric data. So they took all the like different like band things, like, you know, they took the Johnson band, they took the UB, like the other bands, so like all available band they took. So like I forgot these names, like there was something Epsilon band and there was something like
You
these
remember the
bands.
authors? You remember the authors?
Yeah, I had to take right here.
Okay.
Yeah, so it's the Cron Martins and the Moitin Home.
Okay.
To this phone. So because they have like a lot,
That's the first hit with Google. Hmm.
what did
Yeah.
you say?
Okay. Okay. Go on. Go on.
Yeah, okay. So like because they have so many parameters, because all of the parameters they have, like, you know, 5 parameters from the Johnson, 5 parameters from the other one. So they have so many color things. So what they did is, sorry, this was the first one. So they use a method called like it's called PCA, like the principal
Yeah.
component.
Yeah. Yeah.
Yeah, so because they have so many data, they use the PCA and then they select the 4 most important like variables. So like this is one thing that they did first. So every time they take a value, they run a PCA on it, on the photometry data, and then they select the 4 most important parameters in the photometry data, and then they run a clustering algorithm. So here they use the spatial clustering. Or also sometimes they use the like the k-means clustering. So spatial clustering is very close to the k-means clustering. So they use that method for clustering as the clustering algorithm. And once they found different clusters, then what they did is that they compared these clusters with a uniform distribution of like uniform distribution of the photometric like data. So they make a simulated data of uniformly distributed photometric data set. So they say that this will be our field stars. So field stars should be like, they assume that it should be like uniformly distributed. So once they run the clustering algorithm on the like real data and they got the clusters, then they compare these clusters with the field star cluster, like the random uniform cluster. And if the cluster matches with the uniform distribution, then they throw it out. And then they continue to doing that again and again until the list is empty, or they start getting the same thing again and again. So when they when they're getting a similar cluster again and again, but the cluster is not representing an uniform distribution, then they keep it. Otherwise, they will just throw it out. So they will run this process, many times. They will end this process only if they got the same data set, same cluster, more than 2 times, or there is no data left there, something like that. So
Okay, so that Cantat, Gordon, and Castro and all that, they have done that a lot for Gaia data, no? Upmask.
yeah,
Yes, they have actually
yeah.
used it a lot.
So the Atlas is, as you said, like, it's a little bit strict, and it's also actually computationally extensive, but it actually works very nicely because, it's very complex. But the point is, it's actually very nice if we need to work with all this photometric data. We don't actually have access to the good astrometric data, and that's why these are the only things we need to work on. And this is why they need to run the PCA to choose the most important component, and they run the clustering algorithm and all of these things. So there are 2 points I found. Like here, one, they use a PCA, so that's one thing. And the second thing is, their clustering algorithm. So what I saw is that some people use a modified version of Upmask, where they just change the clustering algorithm they use. So in the original Upmask, they use the k-means clustering. So k-means clustering is good sometimes, but sometimes it cannot work very well. So people change this clustering algorithm, and some people also use dbScan, some people use some other clustering algorithm in this particular space. So that's one, that's 2. And for the PCA, I was thinking they had to use PCA because they have a lot of data, and they need to make sure which parameter is actually more important than the other ones. But when we have a limited number of parameter, and if we are confident, by confident I means that we don't have a large noise in our data, so the noise is very small, then I think we can skip the PCA part also and run it with all the variables that we have. So in our cases, or maybe in the cases of the Cantat-Gaudin, I think Cantat-Gaudin use photometric data also. Yeah, so they use photometric data also. They use photometric data, PMRA, PMDEC, and the program motion, all of them. So I was thinking, so that's one. One is we can run the Upmask as it is, and then we can also try to run some modified Upmask where we can change the clustering algorithm, or we can run it without the PCA, because if we only run it with 3 parameters, maybe PMRA, PMDEC, and the parallax, then actually there is not a lot of need of a PCA, because we already have only 3 variables. And they actually say these things later, that one possible future development could be, we can run this method independently on each of the photometric parameter space. So, and then make a posterior distribution. So that will make it more computationally extensive if we use all the photometric parameters, but it will increase the efficiency of the model. And they didn't use it because there are so many photometric data, and they didn't want to keep it running for so long. So they just say that, this is one possible future development. So I was thinking that maybe this is also one thing we can try, but first we can also try with the Upmask itself. So that's things that they use in the Upmask, they just found the most important variables using the PCA, the most important components using the PCA, and they just run a clustering algorithm. Then they make 2 or more different clusters, and once they got several clusters, they compare each of the clusters with a uniform distribution. And if the cluster matches with the uniform distribution, they throw it out. And if the cluster doesn't match with the uniform distribution, they keep it, and they run the model again and again until they get the same thing several times. and they also discuss some math about like how they compare the, like, they use a parameter, which is t parameter, to, make sure like when they will throw out, like how closely it has to be matched with the uniform distribution, or with the, like, the random distribution. So like here in this particular equation, like, this is a mean value for my field listers or the random distribution, and this is the standard deviation for the random distribution, and they use this t parameter as a threshold value, like threshold parameter, to determine like how much contamination they will like tolerate or something like that, like when they will throw it out and when they will not, something like that.
Yeah, I think we all should go through this paper. Then we'd be better off because otherwise we don't know. So maybe Mahmood, if you want on Saturday, on Sunday, you can do both aspects. Do you want to do both aspects? You can talk about this bit as well as the paper. Hmm? Or will that be too much?
Yeah,
Okay, think about it. Think about it and let me
I'll
know.
think about it and
You think about it. I said, right, I'm ready for either because I've given talks on both, so I can do anything. No problem. Okay. Okay, I think we'll have a
Um,
look at all this stuff. I've shared all these links. Okay?
Mahmood,
Yeah.
this site which you have shown, visualizing DB scan, clustering, and various others. Yeah, that,
yeah.
yeah. How can we upload? How can we run these on our data sets? Well, I can't see where we can run it on. There are some samples and all which are sample data sets which are there, but
Here,
can we? From here we can't do that, right?
yeah, here we cannot do that. Like it's just, they made
Yeah.
they embedded it in this website with some sample things.
Yeah, just some smiley face, pimple smiley, and example one. There are some very few ones. Only on that you can run it by changing
Yeah,
yeah.
like we cannot change the values. Like we can just choose between this and that's all.
Yeah. Otherwise, if it could do that, then you could have run them on the clusters which were discussed in the previous paper, and see how this finds clusters and subclusters in that, whether it was agreeing with what you got earlier.
Yeah, like that would be very nice to do. Like here we can also change the like epsilon and the mean points very easily. So like we can,
Exactly. Yeah.
yeah, but the thing is we cannot run it here. That's the problem. So we need to do the hard way.
There may be some other sites similar to this where we can upload your data set and then run these things on that. Because there are many such online calculators and online programs which are available. That would have been good.
Very small, little bit.
It has k-mean clustering and everything there.
It has the k-means clustering and this one. So these two I just found here in this website. But this one is actually more visually like intuitive or very easily understandable.
Yeah. Or maybe R can be used to do these kind of clustering, but I don't know whether it will do it so beautifully as it's being done here. Just by change, yeah. Okay.
So see, I just changed the epsilon from 1 to 0.8 and now I got so many clusters around it. Yeah, so I can stop here this. Yeah.
Okay.
Okay, I think we'll stop over here, right? Because we've had many things today. And we'll go through itself. Mudassir, try to go through those papers, the links, yes, so that we can see. But I think a good idea is to repeat it for with DB scan. No, the code and all is there. Then we can just run it with that data. And see.
So like repeat with the same clusters that we did for the GMM.
Yeah, because then that makes sense, no? If you compare. It.
Yeah, so because it will be easier to compare then.
That's right. That's right. And then at some point we can even try simulated data. If we think that the structure is what is making a difference on the success of the code or not, then we can simulate also some, right? You can say that, right?
Yeah, the structure of the initial structure should make a big difference in how
So
efficient
that's what
these
he's
things
saying, no,
will
that
work.
then we can do it on simulated galaxies.
Or do it on clusters where you have these kind of things very clearly defined, where they are two clusters there, binary clusters, those are examples you can take and run it on those. Take those where you have proper mass segregation in clusters or the binary clusters where, and then run it on that, then those things will work out fine.
Okay, we can check it out. And so next Monday also we'll have to push it because there will be a talk 6 to 8.
Yeah.
Yes, it. So again we can do 8:30 because that is 6 to 8 on 30th.
Yeah,
Okay.
no problem.
Okay, fine. Chalo, so let's meet and we can continue chatting on WhatsApp. Okay. Yeah. Najam, fine.
Yeah, fine.
Okay. Okay, chalo. Okay. See you then. See you. See you later.
Okay, ma'am.